Okay, we'll pick up here with part 2 of the study guide. And, all right, so let's look here at a rotation. You could have memorized coordinates for this, but I always do it by just rotating my paper. So I'm going to physically take my paper and rotate it 90 degrees counterclockwise, so that's to the left. And I'm finding my physical piece of paper. So I'm going to rotate it, turn my paper to the left, and then I'm going to look at where the coordinates are. I'm going to write those down. So when I did that, I had x prime was -4, -1. I had c prime was -3, -4. I had z prime at -4, -3. And then I had b prime at 0, -2. Okay, so now I'm going to turn my paper back, sitting straight up, and then I will just plot these points. Let me go ahead and get a different color to plot the points in. So x prime is at -4, -1. Then at -3, -4, c prime, z prime, -4, -3. And then b prime is at 0, -2. And we'll see if this looks rotated when I draw the new shape. And that looks pretty good. It's been rotated to the left. So counterclockwise, you're going this way, 90 degrees. Okay. A reflection across y equals x. So first I need to show where y equals x is. So that's going to be this diagonal line. Think about if x is 1, if x is 1, y is 1. I'm trying to draw a straight line here. If x is 2, y is 2, and so on, and going through this way. So it makes this diagonal line. So reflecting it is pretty straightforward. I'm going to say how far am I from that line of reflection? So it would be the same if I wasn't doing y equals x, if I was doing the x-axis, how far away am I from the line of reflection? So in this case, I'm going to look here. I am a half a unit away, so that's going to go there. I'm going to count diagonally, 1, 2, and a half. So I go a half, 1, 2, and then I'm going to put a point here. J is a half, so I'm going to go, it's 1 whole unit, so I'm going to go another unit. I'm going to end up there. K is 1 and a half, so I'm going to go 1, 1 and a half, 1. So it's going to end up here, and that's K prime. Okay, connect these up, and we are reflected. Okay, and when you're done, it should look symmetrical. Like if you fold it, if it was a piece of paper and you folded it down that line of reflection, this point should mirror like that. Okay, so when we dilate with a scale factor, I'm just simply going to take the coordinate and multiply it by the scale factor. So 2 -2 times 3/2. Some of you might have gotten confused how to do that. You can always just take your numerator, 2 times 3 is 6, divide that by 2 in your calculator. So in my calculator, I'm going to enter 2 times 3, hit the equals, then divide by 2, and I get 3. So 3 is my new coordinate. It's going to be -3 here. All right, and then I'm going to do 1, 2. So this is E prime. 1, 2 times 3/2. Well, 1 times anything is itself, so 3/2, and 2 times 3/2. The 2's cancel out. I get 3, so that's J prime. R prime 6, 3 becomes 3 divided by 2, that becomes 9. 3 times 3 halves becomes 9 halves. I'm going to turn that into a decimal because that'll be easier to graph. 4.5. S prime 5 negative 2 times 3 halves. That's 15 over 2. Turn that into a decimal. That's 7.5. And negative 2 times 3 halves would be negative 3. Okay, then I just need to plot these. 3 negative 3. That's E prime. 1.5 3. 1.5 3 is going to be J prime. R is going to be 9 4.5. That's going to be off the chart. I'm not going to try to do that one. S is 7.5 3, and it also is off. It's going to be see, estimate it. It's probably about right here, and that's going to be S prime. Okay, so we're looking at shape like this, and somewhere off there. Okay. Translation is probably the easiest. We just move it like the rule says. So 2 units right, 3 units up. You may see a rule like that saying +2 +3. That would be your vector rule. You may see x + 2, y + 3, or just written out like that. So 2 up, 2 units right, sorry. 2 over, 3 up. 1, 2, 3. 1, 2 over, 1, 2, 3. 1, 2, 1, 2, 3. And 1, 2, 1, 2, 1, 2, 3. Okay, so we just reposition that in a different place on the graph. So out of these, the only one that changed its actual size is the dilation. Everything else does not. It's called a rigid transformation. All right, so looking at a transformation that's already happened and deciding what rule it is. So here, key things, I'm seeing this V to V prime is just going over 1, up 1. Let's see if that's consistent. Over 1, up 1, over 1, up 1, over 1, up 1. So this is going to the left 1, -1, and up +1. And that would be a vector rule. Here I'm going to notice that the coordinates are in a different order. That's a kind of a key that it's been a rotation. So how far did G go? Or G went this way. If we're typically, you're rotating that way. B went all the way here. X went here. So this is a 180 rotation. The default is counterclockwise. Okay, this one I can kind of look at it and tell that it looks like a reflection. We have a line of reflection coming right through here. So it is reflected over the line x = 3. Each point is symmetrical, is the same distance from that line. 2 away, 2 away, 1 away, 1 away, 2 away, 2 away. So that's a reflection. And then here, this is going to be a dilation. It's getting bigger. So I really only need one coordinate because it should be consistent. So I'm going to take this x value. C is 2 away, and then it becomes 4 away. So we went from 2 to 4. So how do we find out what is that scale factor? Well, it is image over pre-image. So the image is the after, so that's the green. So green over purple. So green is 4 units, purple is 2 units. So this is a 2-to-1 scale factor. So we could say it is a dilation. I always spell that wrong. Dilation with a scale factor of 2. So the purple one is twice as big as the green one. Okay. All right, this is just 2 transformations in one. So the first one looks like a rotation. A went from here to there. B is going from there to there. So number 1 is a 90-degree rotation. 90-degree rotation. And then from here to here, the coordinates aren't in the same relative position, so I'm going to look for something else. And this then has been reflected over the x-axis. So number 2 is a reflection over the x-axis. See, this is 2 units away, that's 2 units away. Alrighty, which of these is a dilation? Okay, so if you dilate something, it's going to be proportionally larger. So if x is 1.5 times bigger and y is 2 times bigger, that would not be consistent. If I just add 2 and take away 4, that is not going to be a dilation. That's going to be a transformation. A translation. If I multiply it by 3 and multiply it by 3, that's consistent. That would be a dilation. And here, of course, not. You've switched their places. So again, which is dilation? It has to be bigger consistently. So 2 times 3 gets you 6. So just 4 times 3, it gets you 12. So we do have consistency here. That would work. These does not work. 2 times 4 is 8, but 4 times 4 is 16. 2 times 3 is 6, but 4 times 3 is not 10. Okay. A line has 2 endpoints, goes on and on. Array has 1 endpoint and 1 arrow. A line segment has 2 endpoints. We note them like this. And remember, ray is the only one that has direction, so YR would be incorrect. Collinear means they're all on the same line, so we're looking at F, B, and W. The plane in 2 different ways. For a plane, we need 3 letters that are non-collinear. So we could do F, Y, W, any 3 points that are not on the same line but are on the plane. You could have done Y, F, B. Here's what don't do is not F, B, W. Okay. You could have also named it as plane R. The line that's not on the plane is line I. And the intersection of two lines is always just a point, so that is point B. Okay, so partitioning, this is where it gets a little sticky. C partitions a segment with endpoints, so let's just draw it out. Now, it's always a good idea to do these problems on graph paper, because then you might even just see the point. And you might could just count it on the graph. But from A to C to B is the ratio 2 to 1. 2 parts to 1 part. And we need to know what is this. So kind of this, maybe this will be easier because we've been doing ratios. We want a proportion that shows a 2 to 1 ratio between the distances for segment AC and CB. So the length of AC for the x coordinate would be x minus a minus 3 over 6 minus x. That should be in a 2 to 1 ratio. So the length of AC compared to CB for the x term. That's what we're looking at here. All right, so that is, I'm going to cross multiply. So 1 times x minus a minus 3 and 2 times 6 minus x. Cross multiply. X plus 3 equals 12 minus 2x. Add 2x to both sides, 3x. I'm going to subtract 3 from both sides. And now divide by 3, x equals 3. Okay, so we know this point right here is going to be 3. And then the next ratio would be for the y's. So I'm going to do y minus 3 should be proportional to negative 3 minus y. That should be in a 2 to 1 ratio. So that means y minus 3 should equal 2 times negative 3 minus y. Y minus 3 equals negative 6 minus 2y. Add 2y to both sides, you get 3y. Add 3 to both sides, you get negative 3. So y equals negative 1. And like I said, you could have done that on a piece of graph paper, just drawing out the points and seeing where 2 parts to 1 is. That could have been easier. I don't know, maybe. I just don't have any graph on here. But here's one that is on a graph. It's actually saying find the ratio that L partitions. So it's going to be proportional for x and y, so you can really just deal with one of the coordinates. So let's take it also falls right on the diagonal, but we'll just go this way. So from L to M, the x value, the x distance from L to M is 3 units. And the x distance from L to N is 1 unit. So we can say that L has partitioned Mn in a 3 to 1 ratio, or a 3 to 1 ratio, because it's 3 parts to 1 part. If we look at the y's, let's just check those out. It went from, well, it did 3 units again and 1 unit again, which is what you would expect. Okay. So that's why I say sometimes these are easier to do on a graph. The problem before, you may want to do that on a graph too. All right, so A, B, C are collinear. B makes the distances of AB. Let's try this one on a graph just to see. Oof, I don't know, these numbers. I think it would be hard to do without an actual graph. So I'll show you how to do it with numbers, and then you can do it on a graph on your own. So we've got from A is at -1, 3. B is at 5, 9. This one's a little different because they're not giving you the endpoint. C is at XY. So let's find the Y coordinates. So we only have to worry about the Y's. And this is a ratio of 3 to 7. So I want this proportion to be set up. The distance of AB compared to the distance of BC should be in a 3 to 7 ratio. So AB is going to be 5 minus a -1. That's the length of AB. Over the length of BC, which would be, oh, I'm doing X's. I need to do Y's. Start over. So we're going to do 9 minus 3 over Y minus 9, the length of BC. So this is AB. This is BC. And that is in a proportion of 3 to 7. So 6 over Y minus 9 equals 3 over 7. Cross multiply. 42, 6 times 7 is 42. 3 times Y minus 9. 42 equals 3Y minus 27. Add 27 to both sides. 3Y equals 69. And 69 divided by 3 is 23. So Y equals 23. Okay. All right. Now we got a dilation that's not in the center. It says make it a dilation where K equals 3. So K equals 3 means multiply it all by 3. So we want these points to be 3 times further from B than they are now. So I'm just going to count. A is 3 units away. So 3 units times 3, it needs to be 9 units away. So 3, 6, 9 units away is going to put it right here. Okay, D is going to be right in line with A, but it's 1, this way it's 1, 2, 3, 4 away from that. So that needs to be 12 away. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's going to be D prime. And then C is going to be just like D. So we can just kind of line that up. C prime. Okay? So our dilated rectangle is this much bigger. So it's 3 times further from point B as it was. Oh, this looks like some algebra. Y-intercept of y equals here. So y-intercept is always this number. Okay. The equation of a line, so that goes through the point -2, 4. So we need 2 things for an equation of a line in y-slope-intercept form. So the slope comes from the number right in front of x. So this is the slope. So our slope and parallel lines have equal slope. Equal slope. So our new equation is going to have a slope y equals 8x. All we need is the intercept. So how I get that is I'm going to take my equation and I'm going to substitute this point in here and in here into the x and a y and keep the slope. So 4y equals 8 times x, -2, minus 10, but I don't want the same intercept. I need to solve for that. So 4 equals negative 16 plus b, and b equals 20. So I'm going to add b, add 20. So this is my equation that would have the same slope, but go through that point. Okay, this is exactly the same, except we're going to do perpendicular. A perpendicular slope is m, is going to be the opposite reciprocal. So take 8, turn it into 8 over 1, and then flip it and make it the opposite sign. So our new slope is going to be negative 1/8. So I'm going to write an equation that looks like this, but with a different intercept. Okay, so now I need to substitute x and y and the new slope into y equals mx plus b to find my new slope. So I'm going to substitute 4 for y. So 4 equals the new slope, negative 1/8, and x is negative 2 plus b, the new b. Okay, so I'm going to multiply. Negative times negative is positive. 1/8 times 2 reduces to 1/4 plus b. Then I'm going to subtract 1/4 from both sides, and I have b equals 3 3/4. All right, so this intercept is 3 3/4. You could write it as 3.75. Either one would be fine. All right, this construction, I'm going to give you a website that you can go look at, not a website, a YouTube video. If you search constructing a parallel line through a given point, and the video I watched was HCC Math Help. Okay, he uses an actual video so you can actually see the compass. The way I'm doing it is not really as good because you can't see the compass. But what you do here is you start by putting a point, call it B. You take a ruler and draw a line through there. Then you take a compass, and if you haven't remember what a compass is, it has a point on one end. It's a little tool, and it has a pencil on the other end. I have to draw a pencil, and then then it can, adjust. So you put the point on point B, and then you're going to just draw an arc like this going through both, and then you're going to move the point up to A, and without changing the size, draw another arc. I'm going to try to estimate how far that is. So it looks like it's going like that. Okay. Then you're going to use your compass and measure from here to here and set your compass that big, and take your compass up to, this should have extended on up. Put the point of your compass here and draw an arc that's the same size. And then we can connect these 2 points. And then the idea is that these angles right here would be congruent. So those would be corresponding angles. And if that's the case, then these could be parallel lines because we have congruent corresponding angles. So that's the idea of how a construction would work for that. You wouldn't have to actually do a construction. You may just have to recognize the construction and do the next step or something like that, or see what the next step would be. All right, so that's that idea. This last one, basically congruency, is when things are equal in measure. So in shapes, all the same side lengths, all the same angle measures. It didn't change any of the shape or the size. With similarity, you could have changed the size. So something could get bigger, but have still the same proportions and the same angles, and it could be similar. But congruency is not going to change shape or size. And that's about it. So we will see you tomorrow, and have a good night or day, whatever time of day it is. Bye-bye.